So if you've not already done so, which I'm guessing you probably haven't, I would suggest going ahead and drawing what we're looking at here, which is a membrane potential versus time graph. So on the membrane potential, then on the y-axis, you'd be drawing membrane potential in voltage using millivolts. 0 would be up towards the top, maybe like 2/3 up the graph. And down at the bottom, you'd have, say, minus 100. Way up at the top, you have plus 50. On the x-axis, then you would draw time in milliseconds, and you'd basically do 7 milliseconds is a pretty good time course here. So it's milliseconds, which is thousandths of a second. Okay. So when we draw a resting membrane potential, remember that our hypothetical membrane potential is at minus 70 millivolts. And so usually what you're going to do is you're going to start with a straight line right at minus 70. And then in this case, we're going to be going further, and we're going to be describing a depolarization. A depolarization is a situation where the inside of the cell, and thus the membrane potential, is going to become less negative. So if you're drawing this straight line, now you want to draw a bump up. As you can see, it goes in the direction of 0, but does not even come close to 0 itself. And then what you can say at this point, because we're drawing just a local potential or a graded potential, you can just go ahead and drop it back down to 0 and just draw the straight line going across again. Go ahead and draw another one just for practice. It doesn't take long once you start doing them. Again, draw the same thing. Draw your resting membrane potential at minus 70 millivolts. And now you're going to be drawing a hyperpolarization. With a hyperpolarization, the resting membrane potential, and thus the resting membrane potential goes away from 0 or becomes more negative. And then go ahead and just draw it bumping down to, say, minus 75, and then just bump it right back up to minus 70. Continue your straight line. So what we're looking at in both of these cases are called local potentials. Local potential or a graded potential is a short-lived local change in the membrane potential. It's usually mediated by the opening of chemically gated or ligand-gated channels, and this usually takes place in the dendrites. And so we're seeing in our picture here that what we're drawing, or what we're taking our measurement from, is from a voltmeter with the microelectrode stuck directly into one of the dendrites, so that you can see that there's just a small local change that immediately dies out. So the stimulus, such as a mechanically gated stimulus or a neurotransmitter binding to a channel, causes a channel to open, and ions will flow in and out. The membrane potential then changes, and a current passes down the membrane. So from this stimulus locus, the place where the stimulus first occurred, you will have a small amount of membrane potential that passes. So this is what it looks like. You'll have a stimulus in one area. If you have just a small amount of the dendrite that is observed, you'll have a stimulus in one area, such as a neurotransmitter binding. And in this case, what we're showing is that sodium ions are actually flowing into the cell and causing a brief depolarization in this case. And by the way, this is almost entirely every single time exactly the way that depolarizations occur, is that sodiums flow into the cell. Is it possible for depolarizations to happen in other ways? Yes, but almost without exception, especially for the purposes of our classroom, it's always going to be sodium entering. So here we have sodium entering into the cell because some sort of ligand, some kind of neurotransmitter bound in this region, sodium flows in, and what we'll see is that there is a certain amount of current that actually passes down the membrane. In this case, it is not a great deal of current, and so it dies off. So one of the ideas of a local potential is that the stronger the current, the further it will pass. So a very strong stimulus will allow for a greater voltage change and a longer wave of changes. However, if it's not a very strong change, the changes will decrementally die out as they pass, and this loss is due to leakage channels and sodium-potassium pumps regulating everything again. Beyond the stimulus locus, the ions don't necessarily flow in and out, but rather the negative charges are displaced by positive ones and so on down the line. In other words, it doesn't take a stimulus going in and out at every single part of the membrane. Rather, that original stimulus is enough. As long as it's a very strong passage, it will actually go quite some distance.